I'm going to help you get through some problems that you'll find at the end of chapter 16 in the black textbook. I assume it's chapter 16 in the other one as well. The problem numbers may be different, but otherwise they should be the same problems. So let's look at 16.49. And essentially it's asking for us to write a chemical equation for the dissociation of weak acids. They want us to use H plus as a product and the hydronium ion H3O plus as a product. So we'll do it 2 different times for each one. And there's the 2 acids. There's the bromous acid and whatever this organic acid here is. I don't remember if it said the name on the problem in the book or not. Anyway, the first thing we'll want to do is write the dissociation equation or reaction. And for the bromous acid, HBrO2 breaks into H plus, HBrO2 minus. Notice all 3 of those are AQs. And the Ka expression, we put the products over the reactant, and we're good to go. Same way with the organic acid. It's the H plus and the C2H5COO minus all over the C2H5COOH. And that's written rather awkwardly in my opinion. Some people like it that way. It shows a little more about the structure of the molecule to write it this way rather than, the way we do it with like acetic acid or acetate. C2H3O2, this would be C3H5O2 minus. It's a matter of taste. The C2H5 part of it is right here in the structural formula. Then we got the COO there in the center, and then the ionizable hydrogen. That's the hydrogen that makes it an acid. That's the one that comes off in solution if it's an acid, which in this case it is. It kind of looks like a hydroxide OH, but it's an organic acid. That is an organic acid functional group there. So the H comes off. So if we were doing it for H3O plus, the hydronium ion as a product, we would want to have a water liquid on the reactant side with your acid, and we make H3O plus and BrO2 minus, and the K expression will now include the hydronium ion instead of the H plus. Otherwise it's exactly the same and the problems would work out exactly the same way. So when you're doing number 50, it'll work out very similarly to this one. 451, yes, it worked this time. We're calculating the Ka of lactic acid. C2H4OH, that's an ugly formula. pH of a 0.10 molar solution is 2.44. That's worded a little weird. First thing we're going to do is we're going to write the dissociation equation. We're not using hydronium ion this time. You can if you want. Not at all necessary. So we'll write the formula there and the equilibrium with H plus. C2H4OHCOO minus. We're going to make an ice table. We know it was 0.1 molar to begin with. These were both 0. This can only go down by x. These both go up by x. 0.1 minus x, x, x. Then we're going to calculate H plus from the pH. We know if the pH is negative log of H plus concentration, we can rearrange that to where the H plus concentration is 10 to the negative pH power. In this case, 10 to the minus 2.44, which turns out 3.6 times 10 to the minus 3. And we call that x because H plus is x. So if H plus is 3.6 times 10 to the minus 3, then this molecule, or this ion here, is also same thing, x, 3.6 times 10 to the minus 3. So next we'll write out our Ka expression and solve. H plus, C2H4OHCOO minus, because it's products on top, reactants on the bottom. We plug in 3.6 times 10 to the minus 3 for x. And when I work that out, I get 1.3 times 10 to the minus 4. It would be best if you didn't round anything until the very end, but I know that's hard for us to not round at all times. So if you can hold off rounding, hold off, but I didn't either. So number 52 ought to be done very similar to number 51. Let's move on to 53. 53, we got a 10th molar solution. Ooh, we get a little carsick here. 10th molar solution of chloroacetic acid dissociating to the point of being 11% ionized. Calculate the chloroacetate ion concentration, the hydrogen ion concentration, and the chloroacetic acid concentration at equilibrium, and find Ka while we're at it. Now in the black book on page 669, there's an equation 16.27. Looks an awful lot like this right here. It's the hydrogen ion concentration at equilibrium divided by the initial weak acid concentration. In this case, the chloroacetic acid concentration. It's the initial concentration times 100%. We'll plug in 11% here. We'll plug in 0.100 molar here. We got 100% here. We'll rearrange, do some algebra, hocus pocus. We get 0.011 molar for the H plus concentration. We will plug that in our ice table. We know that if H plus is 0.011, therefore the chloroacetate ion is also 0.011 because they're both X. And if one is 0.011, the other is 0.011. And then we'll subtract 0.011 from 0.100, and we get 0.089 molar. 0.089 molar, that is the chloroacetate ion or the chloroacetic acid concentration at equilibrium. So to find Ka, 0.011, 0.011 on top, 0.089 on the bottom. Not a magic, like that one is there, that one goes there, that one goes there. Plug that in, 1.4 times 10 to the minus 3. So the answers are the chloroacetate ion and the hydrogen ion are both 0.011 molar. The other is 0.089 molar, and Ka 1.4 times 10 to the minus 3. That's the answer. Number 54. I think they use bromoacetic acid. That would be very similar to this one. You'll be able to really get through that one good. 55. Oh, we lost it. That happened earlier. I'll have to come back to that one at a later date. Well, maybe we can get it to come up again. Let's try this. It may take me a minute. You got nothing better to do, I'm sure. Let's see. I want to go check the desktop. 55. Gee. There it is. See if we can get it to come up. Come on up. There it is. Come on, baby. There we go. So 16.55 is talking about a vinegar, which is basically just acetic acid and water. It's a solution. It has a pH of 2.90 and a Ka of 1.8 times 10 to the minus 5. We want to calculate the initial. It doesn't say initial. I think it has to be initial vinegar or acetic acid concentration in the vinegar. Right? It says assuming acetic acid is the only acid in the vinegar, we'll calculate that initial concentration. I made an ice table showing the setup here. And we are always using X for the change. So I couldn't use X for how much we started with, so I used a question mark for my variable and how much we started with. So we start with, we don't know. We subtract X, and we got, I don't know, minus X. I know that's very technical. So 0 added X to become X. 0 added X to become X. We know the pH, so we can find the H plus concentration. I get 1.26 times 10 to the minus 3, which is also the acetic acid, or the acetate ion concentration. See, they're both X. And if H plus is X, and C2H3O2 is X, then they're both 1.26 times 10 to the minus 3. Again, if we don't round, we'll probably get a better, more accurate answer. I rounded. Plug it in. Okay, we got our K expression then. H plus C2H3O2 minus concentration over HC2H3O2 concentration. We'll rearrange that because we know H plus, we know C2H3O2, we know Ka. We don't know HC2H3O2. We'll rearrange to solve for the one we don't know, do the algebra before we do the math. H plus C2H3O2 over Ka will be that. So 1.26 times 10 to the minus 3, 1.26 times 10 to the minus 3, those are both X. 1.8 times 10 to the minus 5 is Ka. Plug and chug, I get 0.0882. So question mark minus X is 0.0882. And we know X is 0.00126. So you get 0.08946 moles per liter. Or if you want to do it in scientific notation, which is the better way, 8.82 times 10 to the minus 2 plus 1.26 times 10 to the minus 3, 8.946 times 10 to the minus 2. Here's your molarity. So now we've gone through 49, 51, 53, and 55. I'd like you to do 50, 52, 54, 56. I think you can handle it. I'll be home. You can email me. Jared's pretty good at this kind of stuff too, so he can help you if he's willing.